Good morning. My name is Evan Spalding, and I'm here to present on my thesis entitled Developing and Strength Testing a Natural Fiber Composite for Yacht Construction. First, I would like to acknowledge all those who have helped me throughout this thesis project. First, my principal advisor, Professor McMahon, my reader, Professor Royce, my editor, Professor Harris, and Leo Vasiliev and Vlad Slavinsky from the Northeast Keelboat Alliance for the use of their composite shop and assistance and test specimen manufacture. The objective of my thesis is to develop a sustainable composite of adequate strength to be used in yacht construction. The strength of the composite must be verified through simulation and physical testing. Now I will provide an outline of the topics I'm discussing today. I will first discuss the background and theory behind my thesis, explain the methodology, provide results and conclusions, and make recommendations for future work. Most yachts are built with fiberglass composites, as it has a stronger and lighter construction compared to wood or steel, and allows for construction using molds, which usually provide a more aesthetic design. However, it cannot be easily recycled, which supplies the need for a more sustainable composite to replace it. Natural fiber composites are more sustainable than fiberglass, while allowing for less emissions in their production, but more importantly, their ability to be recycled. Some companies have started experimenting with using natural fiber composites, like the Greenboat's Flax 27 pictured here, which was built with flax fiber 8 years ago and is still on the water. Fiberglass composites are made from reinforcing a polymer matrix with glass fibers. These fibers are sourced from raw materials and formed into thin filaments that are woven into fabrics, either with a fiber orientation or chopped into small strands. Fiberglass is utilized in many industries where a high strength weight to ratio is required. And they are with a utilization of 10 million tons across these industries. They also ensure a load transfer with the polymer matrix and a protection of the fibers. Chopped strand E-glass is a specific fiberglass composite that is used for large quantity, low-strength yacht construction. It has an efficient construction technique with a chopped strand gun that can be seen in the picture, which results in randomly oriented fibers and a low material price. Its strength and price make it a good composite for comparison in the results section of my thesis. There are only a few select natural fibers that are suitable for use in yacht construction. One of these is flax fiber, which also has a long fiber length, high toughness, and a competitive price. Another fiber that fits the criteria is hemp fiber, which also has a high water resistance, more flexible fibers for molding, and a similarly competitive price. There are two types of matrix that can be used in composites. The first are thermosets, which are the traditional matrix that are used in most composites today. The mixing of the resin and hardener, pictured here, results in a chemical reaction that cannot be reversed. Some thermosets can reach up to 30% organic polymers and reach up to 80 degrees Celsius during the curing process, which should not damage any fibers. Some common organic thermosets are unsaturated polyester resin and epoxy resin. The other matrix that can be used are thermoplastics. These are melted into the fabric instead of chemically bonded. This makes them infinitely recyclable. They are not often used in high-strength composites due to their slightly lower strength. However, they can be fully organically based, and they require 200 degrees Celsius to melt, which could possibly damage the fibers. Some common organic thermoplastics are polylactic acid and poly-3-hydroxybutyrate, which have similar properties to plastics used in the petrochemical industry. The law of mixtures was utilized to provide the material properties of the overall composite from individual fiber and matrix properties. This utilizes the volume percentage of each component to estimate the breaking stress. Some limitations of this law are that it is a very simplification of a complex structure interaction. It is intended for homogeneous and idealized composite structures, and it is often employed as an initial approximation in engineering analysis, which is how I used it here. It does not account for the fiber matrix interaction or any defects in manufacturing. This leads into that finite elements analysis, which is where the material properties were inputted from the law of mixtures. It is an engineering simulation for structure interactions, where a large structure can be divided into small mesh elements so that a mathematical analysis of complex structure is possible. I use SolidWorks FEA because of its capability to analyze composites, simplicity, and availability for me here at Webb. To manufacture the test specimens, I used 180-gram flax unidirectional fiber and a bio-based laminating epoxy. This is the tensile test panel with a 4-layer laminate resulting in 1.6 millimeter thickness. I also constructed a bending test panel with a 9-layer laminate and a 3.3 millimeter thickness. The layers of fibers are laid 90 degrees apart for each layer, and then vacuum bagged to remove the excess epoxy and air from the composite during the curing. Once these panels were cured, test specimens were cut from each panel. Some were cut at 45 degrees to achieve a negative 45, positive 45 degree fiber orientation, as can be seen here in the tensile and bending test specimens. Some were also cut at 0 degrees to achieve a 0 degree, 90 degree fiber orientation, where optional cap strips are utilized to reduce stress concentrations caused by the tensile test grips due to the higher tensile strength of this fiber orientation. The tensile test I utilized was the ASTM D3039 standard test method for tensile properties of polymer matrix composite materials, as can be seen in this picture. It is a basic test to determine tensile properties where the specimen is clamped and secured with friction and stretched until tensile failure. The FEA model does not model the compressive force of the grips onto the composite, but it does use a distributed tensile load over the same length as the grips. This simplifies the model as the compressive load does not make a significant difference on the overall breaking stress. The ultimate goal of this test is to find the ultimate tensile strength. For the bending test, I utilized the ASTM D790 flexural test of plastics and composites that can be seen here. It measures the flexural properties under a bending force. It is a 3-point bending test where the span is 20 times the thickness, or 60 millimeters. The goal of this test was to find the flexural strength of the composite. Shown here are the bending test stress plot on the left and the tensile test stress plot on the right, in order to see the stress distributions over the specimens. Here, the point of maximum stress for each test can be seen. Another important observation is the necking that occurs in this test, indicating a plastic deformation of the composite. Displayed here are all the results from the FEA testing. It is important to notice the very low tensile breaking stresses when the strength of the PLA matrix is put under the most stress in the 45-degree fiber orientation. The strength of the flax epoxy composite is the highest for each test, so I will be utilizing only this composite for physical testing. The results of the physical tensile test can be seen here. The results are displayed as an applied load over time. The 0-degree fiber orientation, shown in blue, has little plastic deformation and a much higher breaking stress, while the 45-degree fiber orientation, shown in red, has a much more plastic deformation and a lower breaking stress. This is due to the lack of continuous fibers and the lower strength of the matrix in the 45-degree fiber orientation. Here we can see the results for the two bending tests. The results are displayed as an applied load with function of position. Once again, the 0-degree fiber orientation has a much higher breaking stress due to the same factors as the tensile test. In this video, we can see the bending test in action. The discontinuities on the 0-degree fiber orientation occur as a result of the individual plies of the composite fracturing under the high tensile load at the bottom of the composite. It is also important to stop the bending test at this point to avoid frictional forces involved with hitting the edges of the apparatus shown here. Before I discuss these results themselves, it is important to note that the physical flax epoxy composite is only 25% as dense as the predicted value that was used in the finite elements analysis. So to give a better comparison, the breaking stress was divided by density to show the strength per weight of the composite instead of the strength per volume. Error with the 45-degree fiber orientation is due to the law of mixtures, as it does not accurately predict the strength at an angle from the fibers, since it is a laminate composite instead of a homogeneous composite. The same trend can be seen here with the bending test. Here we can see a strength comparison between the chopped strand E-glass and the physical flax epoxy composite. The flax epoxy composite is weaker in the 45-degree fiber orientation, as the chopped strand has a uniform strength in both directions due to its random fiber orientation. However, the bending is the more critical strength loading for yachts, and the flax epoxy composite exceeds the strength of E-glass when the 0-degree fiber orientation is utilized. Some conclusions of my research are that the 45-degree fiber orientation has much more plastic deformation due to the stress being placed more on the matrix. This results in large inaccuracies when utilizing the law of mixtures. The strength of the composite is when within 20% of the chopped strand E-glass composite, which means it has adequate strength to replace chopped strand E-glass when utilizing stronger fiber orientations, as long as the yacht builder is willing to sacrifice ease of construction for a more sustainable composite. Some recommendations for future work are to develop a more accurate FEA model based on the properties of the fiber and matrix separately instead of using the law of mixtures. Also, it would be good to test a greater variety of NFCs and fiberglass composites for more comparisons between composites. It would also be good to develop an FEA model with natural fiber composites to analyze the strength in an actual yacht design. Thank you for listening, and now I would like to invite Zain up to present his thesis.